evaluate sine fifth x cosine seventh x dx. Here we can afford to leave either a sine x left over and translate the other sine to the fourth x's into cosine x's, or we could leave one cosine x left over and translate the other cosine to the sixth x into sine x's. What I'd like to do is actually leave a sine x left over. And the reason why is there'll be fewer sines to translate than there would be cosines to translate. So let's do that. We're going to write this as sine fourth x times sine x times cosine seventh x dx. And then we'll use our usual trigonometric identity. 1 minus cosine squared x would be the equivalent of sine squared x, but since we have sine to the fourth, this itself is going to have to be squared. So what I'm going to do next is write my cosine to the seventh x, and I'll put my sine x down at the end where it belongs with a dx. So multiplying this out, we get 1 plus 2 cosine squared x, make that 1 minus 2 cosine squared x plus cosine fourth x multiplied by cosine 7x sine x dx. Multiplying through by our cosine 7 gives us cosine 7 minus 2 cosine ninth plus cosine 11th x times sine x dx. And this can all very easily be solved with a substitution u is equal to cosine x. Du is equal to minus sine x dx. And so we get minus integral cosine to the seventh just becomes u7 minus 2 u to the ninth plus u to the 11th du. And now we find each antiderivative. We end up with negative u to the 8th over 8 plus 2 u to the 10th over 10 minus u to the 12th over 12 plus c. Finally, we substitute back our cosine x, and we have minus cosine 8x over 8 plus cosine 10th x over 5 minus cosine 12th x over 12 plus c.